Hello everyone. In this video, I will walk you through how I perform protein DNA analysis in image matrix. Here I'm showing you from my thesis project a diagram of how and what kind of properties of protein DNA complex that I'm analyzing. So here I'm showing you an image of a protein DNA complex. And as you can see, there are two proteins on this piece of DNA. So these are the properties I measure in this AFN image, and they are stoichiometry, which measures the number and the oligomerization state of the protein DNA complex. Number is easy, like that's two complex on this DNA. And the oligomerization state, which means how many proteins in each complex, can be measured from its volume, which is simply area, the area of the protein complex times its intensity. So from the volume of the complex, we can determine how many proteins are there by simply normalize that. For example, in this free protein, we have a much larger volume than all the others. This may be composed by 2 or 3 proteins, right? Versus this one, if this is a single, like the smallest unit, you normalize the volume, that would mean it has one protein in this complex. That's how we can tell. The next property is the position, which measures specificity of protein DNA binding, which I'm going to talk about what that means. So basically here is I'm just simply measuring, I can basically make a profile or section, if you want to call that, along this DNA molecule, which is indicated by this blue line. Along this profile, we can identify 2 peaks, which represents their intensity. So 2 peaks here indicated by these 2 different colored arrows. And we use the location of the peak to identify where the protein is positioned along the DNA. Okay, so the next property is DNA bending and protein DNA coordination. These are the conformational properties of the protein DNA complex. So DNA bending measures the protein DNA interaction interface. So here is basically how much the protein orders the DNA's path from its original path, how it deflects that. So this is like 40 degrees. Here is it deflects the DNA but bend it 40 degrees. Okay, it's deviation from its original path. That's DNA bending. So this is like a 2-dimensional conformational property. So it may not represent what it truly is inside, how it really bends inside the protein complex, but for our purpose, it's usually fine because in AFN, we are if the protein lays flat on the surface, that's the 2-dimensional bending usually is a good representation of from other studies like in crystallography, right? So this is usually a good indication for flat features. That's when the protein lays flat on the surface. And then we also have protein coordination. Okay, this measures basically the other kind of conformational properties. For example, how, like in this case, there are 2 proteins that's neighboring each other. So how the 2 proteins interact with each other on the DNA. Right? This is, I call it association. So it's like beads on a string, but the beads bump to each other. Right? So that's that conformation. And the other conformation you can see is the looping conformation, which you can have 2 proteins bring 2 DNA strands, different parts of the DNA strand together, and it forms a loop. So these are the other properties that we can measure in AFM. Okay, so now let's delve a little bit deeper into the position analysis. So we have this section profile, which I'm going to pull up here. So Now, this is useful to identify the location of the protein on the DNA. So why that's important, right? So just imagine if you have a artificially designed DNA substrate like this two. I mean, that's this double helix, right? DNA is double helix, right? So you have one strand that has a DNA mismatch or a bubble or slip out, a kind of a structure there, and the protein could preferentially binds that structure, so it prefers that, right? So that when it binds to that structure, it forms a peak here. And if you count each one of this location, then you can combine all of these position readings and form a histogram, right? They will give you a distribution that has a peak at the center of this structure, right? And in my analysis, I can measure the I call it short arm length, which is the location of the peak to the nearest distal end of the DNA. So that's D here. And since my construct of DNA, I cannot distinguish which end it is. So it could be from this end, it could be from that end. So that end, essentially, there's no structure. So this is like a false positive, but I measure them anyway. Because the protein has a high specificity, which basically means it has a high binding affinity to this site, which I call a specific site. Okay, this structure here. So you basically get it when you do a position distribution, you get a dominant peak, right? So this is that this purple one represents the position probability of the protein binds to the specific site over a background, okay, non-specific binding events like this pink one. So you can basically deduct, right, from a mathematical model how to do that. So I'm not going to delve deep into that today. So that's just basically let you know. So we measure the short distance, okay, and we probably also measure the fraction of the short arm distance. For instance, if the slip out of the specific site is at, for example, 39% of the DNA, so we measure that as a fraction of the whole DNA length, right? That's the fraction short arm distance, right? So that's the position that we do for my analysis. Now I'm going to show you how to do such analysis in image metrics. First, let's try to open some images. I use image browser, and inside image browser you can type in the address, like the where you store your files, um, and you can also pin your files to this quick access bar. I already have my folder pinned, which is called A6B here. I click that, and that navigates directly to the folder where my files are. So I have these files. Let me open a few images. Yes, let's open, for example, if I want to process one image, right, or multiple images. So you can do multiple images at a time. So let's do like 2 images, right? I can do 3 or 4. Just select all of them, right? So that's how we do that. And let me right click that and select open with. I'm going to open this with image processor. So it will import these 2 images into image processor. There you go. So right now I am inside the image processor. I have these 2 images open here in this, you can see in this tab. So then I will process this image. I just get rid of the artifacts and make the image flat. The typical AFM image processing stuff that you all learned when you do some AFM image. imaging, right? So in image metrics, you can do this manually or automatically. So in this tutorial, I'm only going to do this automatically. I have a script, a macros, I call that, right? Written. So it's essentially it's an automation of the steps you take to, to process this image, right? I already have that, the automation, the macro written for you, and so I could just load that automation utility, the script. So to do that, I'm going to click miscellaneous tab, and then under my apps, this is where you can load your own script, macros, I call that. So this is image processing there. That's my script. And if you cannot find this, you can simply add app. I just show you where you find that. So it's under the scripts folder inside the image metrics program folder sources. Okay, so under that scripts folder, you can find this, I think it's called image processing.mat. Okay, that's macro. That's what it means. So this is the one that you want to add. And then click open. Since I already opened that, I'm going to cancel it. I'm going to directly click this. Okay. And this will let you, ask you a few questions. So, let's not do that for now. And so before you do the macro, okay, the automation basically. So you have to configure a few things. First is, let's see. Yes, you have to configure the size of your, so you want to tell the program, okay, what's the size of the feature that you want to analyze, right? So you want to filter. You don't want to analyze everything, right? There are free proteins in this image. There are also DNAs, for instance. Let me just zoom in a bit so you can see a little bit better. Click zoom. So you have a bunch of stuff here, right? So we are only interested in analyzing DNA. So we want to know the size of the DNA, so we can filter other things out, right? So to know what the size of the DNA is, for example, this piece of DNA, let's just zoom in a little bit further. And I simply can just right click that, just right click the mask. It's not well connected at this moment, but it's okay. I just need a rough figure for that. And I just right click that and click mask and say properties. So I want to tell you, it'll bring up the property of this mask. Then just clicked. And so the one thing I want to know is the area, right? That's so I can just simply use this one, 618. That's the area in pixels. Or you can use the real number in meters square. So let's just put it here. So this is the number I want to use when I filter my image. So I also pay attention to the protein, right? We don't want a free DNA. We also want DNA that has a protein on it. So we have to we need to know that the intensity of this, the highest point of this DNA, which is on the protein, right? So if you move your mouse pointer over the protein, you can see that on the bottom left corner, you can see it's X, Y, and the Z. And right now the Z reads 1.48 e to the minus 9. That's 1.5 nanometer. So that's the height of this protein. So that's another filtering parameter that you want to use to identify the protein DNA complex. So now we have these two important parameters. Then we can basically click the mask filter here and set up our filtering parameters. So now I have this area, which is the area in pixels. This is this number. So I've set it up. Okay, I think this is for the not in pixels but in the real unit. So this is area real. So that's e to the minus 15. So right now it says as 2 because as I said, this DNA is a bit truncated, right? So it's not well connected into this mask. So we would have to use a bigger number, and this is a number I would typically use. It's 4e to the minus 15. It's a little bit bigger than the 2.3 e to the minus 15, but that's the number that I use to filter my DNA. So once I process this image, right, this mask will be it'll be well connected, so it will mask all the DNA, not like its current state. And then the max intensity, which is the height of the protein, and I just we just saw that it's like 1.5 nanometer, so I just use a small number. So 1 nanometer is a good number to filter the protein bound DNA. So that's what I use. So I already set these two numbers, and if you don't see these parameters, you can basically click filters and choose the parameters, right? Then click OK, and okay, and then I also want to do is the auto threshold method, right? So this is the method. This is the thing. This is the parameter. I mean the option. I mean the stuff that I need to threshold my image, right? So I mean you can either do that by manually enter a threshold number there. This is determines how you would mask the DNA, the DNA protein complex. Um, so the red mask is determined by this threshold number, right? The higher the threshold, the mask will become smaller, right? So it only masks the higher features, right? And the smaller, and it will mask more of the protein complex, right? So you can either do it manually or do it automatically by using this auto threshold method. I use auto threshold method. So this is the method I use. It's called Gaussian. So basically, what it does, it fits the intensity of the image into a Gaussian curve, and you have the dominant peak, which represents the surface, and can fit that surface into a Gaussian. And this is the parameter I usually use. Is from negative 1 nanometer to positive 1 nanometer. That's where the range of the surface is. I fit that to a singular peak, and I mark the threshold cutoff. Okay, that's the intensity I use for my mask, which is like 1.4 standard deviation from its center. So I fit that to a Gaussian and calculate its standard deviation, and then I use 1.4 standard deviation from its center of the peak, which is the surface level. Use that number to determine my mask value, right? My threshold value for my mask, and that usually works very well across all imaging conditions. So, yes, so this is how I do that. I can talk more detail in another video, but I'm good for now. So we set this up. We click OK, and so these are the two steps that we need to set before we run our automation. So once that's set, let's go back to the miscellaneous tab and click these. So okay, let's just zoom out for now so you can see them better. All right. So let's click my apps and click image processing. Now you select the images you want to process. Now we only have 2 images. I select all of them, and you can imagine you can do this in batches, right? You can do 10 or dozens of images all at once. It's a choice. So I select that, and then I select the image channels I want to process, right? So I usually use just pick the one that you want. You feel like, I mean, when you see your images, which one looks better in your eyes, right? And this image, the height retrace looks better, so I pick the height retrace. And now it's processing the images in the background, so you can see these in the bottom status bar. There are like 32 steps. Now it's at 0%, and now it says, Okay, so we're at step 1, step 2. We're on image 1, we're on channel 1. Okay, and then when we only process one channel, and this is like 16 steps in the macro. And I'll talk more about the macros and what this automation does in another video. So you can customize the macro. Essentially, it's composed by different steps, right? And the steps is laid out here. Okay, right now we are flattening these, right, and height ratio is channel in this image, and you can just find what the macro is doing right now. Like we have flatten order, flatten direction, and flatten this again. Right, so this is description of the different steps in the macro. And then we can link the protein fiber, the DNA fiber, if it's disconnected. Then apply the filters. Remember the filter parameters that we just set, right? The area and the intensity filter. That's how we get rid of this free protein and DNA. And to identify our protein DNA complex, which you can see here is labeled in different colors, and they are well connected. That's exactly what we want, and we are doing particle analysis. Now it finishes an analysis. We identify 118 particles, and it's labeled. Now it moves on to the second image and repeat the same steps. Now I have finished all the particle analysis on these two images. Okay. Again, just in case you're wondering what does the automation do, I'll post another video on that. Now let's see how this processing look. How does it look? So we can zoom in. Just run. Just scroll your mouse wheel. You can zoom into an area, and you can see the DNA are well masked. And some of the DNAs they're masked together. But that's not important for our purpose because we're doing single molecule analysis eventually. So all we need is to make sure they're connected instead of disconnected, right? They're connected in one piece, and then we can pull individual analysis on them. That's the most important, right? We don't have to separate them at this point. We're not doing bulk analysis. We're doing single molecule analysis eventually. So now let's go to the single molecule analysis module, which is the region inspector. To do that, let's go back to the Analyze tab and just click Region Inspector. So this will bring up the Region Inspector app. Now we're at the particle 1 here. So let's get familiarized with the interface of Region Inspector at the moment. So as you see, the window of the region inspector is synced with that of the image processor. So right now we have the same view as you see in the image processor. We are viewing the same molecule, region inspector as well. And now we are at particle 1, which is this guy, right? Particle 1 is labeled there. So I have like 120 particles. Now we are at particle 1. You can navigate the images here, right? Image 1 to 2, and the particle list here. Now, so you can see there are 120 particles. Exactly what we find in the image processor. So also make sure that the autosave sections are checked, and we'll see them in action later on. So basically, it will save your measurement automatically when you finish measuring the particles. Now I have all my tools laid out in this toolbar. I call it new toolbar. And they may ask, how do I get these tools in a separate toolbar? So what I did is I right click the tool strip. And I can basically create a new toolbar. And so that's how I get a new toolbar. And if you want to put your tool into this toolbar, you can simply right click a tool and then say click add to a toolbar of your choice. So I'm not going to do that right now. So I have already have my tools added. And if you need to find the tools, you can find these region of interest tools ROIs on the Analyze tab. You can add them manually. And these mask tools is here in this mask and also in this mask tab as well. And they have the draw angle tool under in the Analyze tab. And if you want to add the link DNA, which is a useful tool, if the DNA are disconnected, like in the mask, then you can simply right click the toolbar and click add function. And then from that, you can search for link DNA and add it here. Now we're at particle 1. So you can see that particle 1 is this whole masked area. It can actually contains 2 DNA molecules here. So we need to further dissect particle 1 into 2 separate single molecule analysis. Now, first, let's click on one of the DNA. And so you can see it's tracing the DNA along the mask. Now, if you want to know how does this tracing works, you can simply turn on the mask. And now I make the mask transparent so you cannot really see them very well. You can adjust the transparency under the mask tab. So here I have these. I can make it lower. Now you can see a little bit of the mask better. Or you can just turn off the transparent mask. I also put it here. So if I turn it off, then you can see the mask better. And as you can see that if the masks are continuous, right, it's shared a singular color. And you can also see the skeleton of the mask, and that's where we make the DNA trace. So you see the DNA trace follows the skeleton of the mask. So I like to make the transparent mask on. Let me see the molecules. I like to make it 0.9 here. So let's just go back to the original value. So yes, if you want to see mask better, you just simply turn off the transparent mask. Now you can get that, right? So, all right. So now, since there are 2 DNA molecules, let's first try to refine our trace into only the first one. So now we have the trace that starts from 0.1, I call it anchor, okay, and ends at 0.2. So we can move this anchor point to one end of this first DNA molecule, which is on the left, and move the anchor 2 a little bit close to its end, okay? Now the quality of the trace depends on how well you mask the DNA. Now this image is already flattened because we already processed them in image processor, right? And now the only thing we need to do in terms of further processing is really just to make sure you mask the particles well. That you want to analyze. You probably have to remask the thing using the mask threshold. Like we should know an auto mask, or just manually adjust the mask threshold here. And now, yeah, turn off the transparency of the mask and see how well you do. All right, so I have the first molecule traced. So you can see there are 4 proteins on this DNA. protein complex. Okay, so these two are small one. They can also be indicated by the height of the peak, and also as well as their size. You can see them directly on the image. And there are the two big ones, one at the end and one in the middle. And so now we want to identify the peak location. Okay, so in image metrics we have a tool and write a custom script to identify the peaks automatically for you. So that's the find peaks. Yeah, and also there's find peaks and spans. These are custom scripts. I will explain to you what they do in more detail in another video. But right now, we just need to know this is find peaks and span. That's the script we're going to use. And if you cannot find this script, you can click load profile, and it's located under the scripts folder inside the image metrics program folder. Okay, so if you go under the scripts, you can find all these scripts. Okay, there are find peaks, and that's what we need. Right, we're going to find peaks and spans. Now, find peaks only finds the location of the peaks. Let's cancel that. We already added this profile. And find peaks and spans. So not only the location of the of the of the of the protein, right? Peaks, but also the span of the protein complex, meaning the entry points, where the DNA goes into the protein, right, and the exit point where the DNA exit the protein. So, and why that is important? Let's go back to our figures. So here I have this protein here, right? Because the protein has a size, if it's small, then it does not matter to our precision, right? So if it binds to this structure there, DNA slip out right there. So if the protein is small, then the peak would corresponds to where the slip out is, right? But if the protein is big, like with multiple proteins there inside this huge protein complex, now you have the inaccuracy, right? So the peak of the protein, right, could be anywhere inside this protein complex, right? It could be from the left edge to the right edge, right? So the peak of the protein complex does not correspond to the location of the slip out. So that leads to inaccuracy, right? So we will not know, okay, whether it's exactly binds to this specific site or not. That's why we need to know that's why we need to know the span of this protein complex in yellow here, right? So I have the left span, which is the entry point, and right span, which is the exit point, right? So it's very useful for us to ask the question whether it binds the specific site or not, right? I have the specific site labeled in orange here. I call it a specific region because there's errors, right, when you identify the specific site. For example, if you at 39% of DNA length, the DNA length measurement has some kind of standard deviation, right? It's not a uniform length when you measure that. So I add a plus minus like 4%, so I get the specific region. And because it's symmetrical, right, we don't know whether it's on the left side or the right side. So I have two specific regions that corresponds to the specific site. And as long as our protein complex, right, its span has crossover between, right, its span and its the specific region, then we say, okay, the protein, I mean, it's probably, it binds to the specific site, right? We call it a specific complex. That's why how we determine this complex type, right? If it has a crossover between the specific region and the protein's span, then we say it's a specific complex. All right. If there's no crossover, we call it a non-specific complex. It's also useful for shortening the DNA. So imagine in your molecules, right? So there could be DNA inside this protein, right? Especially if the protein is very big. So we're not measuring the full length of DNA, but some of DNA is hidden right inside maybe it's supercoiled inside this, right? You don't know what happens inside this protein. So it gets truncated inside the protein. So we have this shortened DNA, and we could add them. We could add them inside this protein complex. So we call it missing DNA there. So that's useful, especially for big complexes, right? It's important information, right? We can add those missing DNA inside our protein complex. So that helps us identify whether make it amount measurements more accurate and determine whether it occupies the specific site or not, right? Because if it's shortened, right, if the DNA length is shortened, it affects the accuracy of our precision measurement, right? But when we add the missing DNA back, it helps improve our accuracy. Now, I'm gonna go into detail of that method. So right now we have these the protein trace, the DNA traced here. I simply right click my profile, which is here. Okay, we have C is like a 330 nanometer, which is about the right length of my DNA. So I have two DNA in my images, two types of DNA. Okay, one short DNA that has the specific site, and one long DNA, which is just homoduplex, right? It's so one heteroduplex and one homoduplex. So right now the 330 nanometer DNA is a heteroduplex, so it has the specific site. Okay, so what I'm going to do, I'm going to click this and find peaks and span. And the other thing I would like to do is I want to determine whether my complex is a specific complex or not. And as I just mentioned, right, if it has a crossover between the proteins, the peaks, span, and the DNA specific region, right, then we say it's a specific complex. Otherwise, it's a non-specific complex. Now the program can also do that automatically for you. I write a script especially for that purpose, right? So it's like I call it trace the post process PD type. This is a custom script. So basically, what it does is it uses the information you recorded, right, the position information, and it do some calculation and figure out whether it's a specific complex or not, right? For example, in this specific example, right, this script does is it calculates the fraction position, right, of your peak and see if it's near this, if it's within the range of 39% or not. Right, 39 is where my sleep where I expect my sleep out is. Now, if it's within 39%, plus minus, for example, 5%, right, it labeled that as a specific complex. And this is not exact measurement as something I just showed you right now using the crossover. It's not. It's just using the location, the peak, and give it a little bit of error, like plus minus 5%, to determine whether it's a specific complex or not. Right. So I have not done the more complex calculation here. It's just a simpler complex. So in the end, you would have to process them again, for example, Excel, to calculate those more complex calculation, like the crossover thing. But you can also do it here if you can customize the script and do it for you. So that's up to your choice, right? So right now we're going to use the simplistic one. So it may not be accurate, but it's useful to, let me know as I measure this whether I have a specific complex or not. If you cannot find this profile, you can click load profile, the same thing. It's also on the script, you can find that. So I have this already checked, which means that it will do this calculation after my recording. Okay, so I'm just going to go ahead and record this, find peaks and span, and see it in action. So I click that. All right. So so what we see right now is as you see the DNA curve, right? The profile has been sectioned into, has been cut into different sections, and it has different color labels, as you see that. And if I zoom in on, let's say, on the first peak, okay. So in the first peak, I have the one here, right, the screen label, right, that's this the very first section. And now I have the orange one, which is from 2 to 3. That's the entry point, exit point of the first protein complex. So it's already automatically, it automatically does that for you. And now I have the second peak and third peak, so it's the same thing, right? And this is a very high accurate process, and you can determine the cutoff in the script. I mean, what's the cutoff of the DNA molecule do you want, right, to determine its exit and then enter an exit point. And I will cover that in another video for that, exactly for those scripts. But right now, you just see the result, right? So it's from 4 to 5. So that's a pretty good job. And so next thing I do, you can also manually adjust the anchor points. And if you want to, if you see, okay, the results is not great, and you can simply move these anchor points, right, and move to a specific location. Like for example, here, say, okay, that's my exit point. Let's say that, okay. And then you can basically click this and then click that record peaks and span again. So that would basically use your manual anchor points to determine the just redo the location measurement. And now this time we'll use your manual position as your exit entry point. So now this is the table that we just recorded for this section, the fiber section. So now you can find all this information, like, okay, so we have the height of the peak, the PD type, the protein DNA type. Okay, all of them are non-specific complex for my calculation. Yeah, so I also have position, reading, and the short arm. So I mentioned that before. The short arm, which is the location of the peak to the nearest distal end of the DNA, and the total length. Yes, I also have the span right and span right. Just mentioned. Now, span left is from the left side of the peak. Okay, the entry point. The span right is the exit point. It's to the right side of the peak. So I have all these measured. And XY would be the XY in pixel coordinates on the image. Okay, so we're going to use that information for later on for very important function. Let's zoom out right now, and yeah, I can zoom in again. So the next thing I'm going to do is to measure the protein, the different parameters of the protein complex. So to do that, I can use the region of interest tool. There are 3 of these, and I mainly use the draw region of interest tool. So click that, and I can draw just by hand. Along this complex. Okay, I can do the same thing for the remaining of these protein complex. Well, notice that the cross mark, right, the marker, is color labeled according to their sequence along the DNA trace. So you know, like, exactly what's the first one, what is the second one. And it corresponds to the rows in this table, right? The first one, like this, would be the first row, and the second one would be the second row. So that's the correspondence. So after I have all these cropped, and just, if you are worried about whether if you can click on one of the first particle, right? So if you're worried about whether this is has the full size of the complex you want to measure, right, you can simply turn off the transparency of the mask. Now you can see that, right, it's already masked pretty well. So that's my first complex, right? So what I'm going to do is I'm going to put this information, right, the parameters of this complex, including its volume, area, intensity, right, all this information here. So I'm going to put it down into my records table and select the first row because that's where this complex should be, right? So put this information into the first row. So select the first row, then right click this matrix table and click record all parameters. Okay. So now you see that the table has expanded and it includes all the other informations like it's in the first row. So we do the same thing for all the remaining complexes. Yeah, make sure you select the row. If you don't select the row, it will put into another row, and we're going to delete that. So that just this third one is not recorded. So I'm going to redo that again. All right, now we have all the complexes information recorded. And I have pinned the columns to front the volume column. And you can see that the first complex is 500 nanometer cube. All right. The second complex is about double or triple, right? The first complex. So that's like 2 or 3 proteins. And the third one is about 1 protein. How do I know that? Okay, because I did another deposition of the proteins alone. So I know exactly what that size should be. It's about 500 nanometer cube. And the last complex is about 2 protein size. So, and I also have my protein DNA type, and all these non-specific. This is calculated, like I said, from the short arm fraction. So in here we have the short arm fraction, that's 16%, 49%, 24%, and 5%. So this is all way beyond the 39%, right? For my specific site, right? That should be around 39%. So that's not around plus minus 5% of 39%. So that's why they're not specific complex, right? They're called non-specific complex. That's labeled for us here. And the next thing I'm going to do is I'm going to measure the angle, the band angle of the protein DNA complex. To do that, I first remove the region of interest. Then I click the draw angle tool. And now I can draw an angle. And to do draw that, just start from the center of the protein, right, and draw towards the edges. So you draw the first one, then you draw the second one, and then it will show up the numbers of the band angle. Now this is not the exact band angle; it's the angle between the 2 DNA arms. Right, the band angle is the 180 degree minus this number. Right, that's the deviation of DNA from its original path. That's the band angle. So we're going to use this one. We'll do the band angle calculation once we export the table in Excel. So, or you can make your own scripts here. Just let it do the calculation for you. So right now I'm content with just use this number for my angle. So I select as well, right? Just if you want to put the angle into one of the rows, right? Just first select the rows first. I select the first row by just clicking one of the cell and right click the angle and say add to angle 1. So the number is put there, and do the same thing for the remaining angles. Yeah, I can just let me just finish drawing this first. And notice that the last protein has no angle because it's the end protein. So we're not going to measure angle for that one. And I'm just going to simply write the confirmation column. Now, this is a custom column that I use. Now, if you cannot find this column, you can simply click the fields here and type like confirmation, like that's, then click enter, right? That's how you add additional column for the table. So right now it's already added there. And if you want a specific column, let's say area, right? If we want that, if we want to put that in front, right? You can pin them. You can simply right click this table and then click the pin columns. Which is here, right? Click the pin columns, then you can select the columns where you want to pin to the top. So this last coding, as I said, it's like an end binding event, right? It binds to the end of the DNA. So I simply say the confirmation is end, or E, as I use short for end. All right, so I get the band angle, the position, and yeah, so that's my first molecule. And so the next thing I want to do is, I think for now, for the basic stuff, that's pretty much it, right? I simply right click the molecule and say record current measurement. So my measurement right now is in the blank, in the dashboard essentially. It's in the selection, right? This is the first one, it's blank. If you don't record it, it will be in this dashboard state, right? A blank state, so it's not recorded. So if you want to record your measurement, you say, okay, you simply right click just anywhere in your image. Usually I would click, just since we have two DNA here, I want to make them distinct, right? So I want to put my record label near my DNA just measured. So I'm just right click here and say record current measurement. So this will put a label here. So that indicates that my measurement corresponds to this, it's called particle 1, or you can call that, right? It's called record 1, right? So right now we are at particle 1 here, right? Particle 1, but particle 1 has two DNAs, right? This is called, so inside particle 1 we have two DNA. That's the first DNA called record 1. And it's also, once you record that, you can change the results. It will automatically record it into the record 1, so you don't have to worry about that. It's automatically saved to the record 1. And you see that in the selection, right? Before it's empty, right now we have the 1 here. So for example, if we go back to empty, which is the blank state, it's the same thing as you say right click and click new blank measurement. That's the same as like click the blank here. That's the new blank measurement. Now that the record gets cleared, right? So you can start a new measurement here, and then do the same thing, for example, for the second DNA molecule. Finish a measurement, and then right click and say record the current measurement again. Then you have like 1, then it will be put into 2. So that's how you do this. Now, if you want to go back to the original measurement, like 1, so go click 1 here, then your measurement will pop up again, right, in this table. So let's and before I go to measure the secondary molecule, I have one last work to do, which is to add these protein DNA complex into another particle set. I'll explain what that means, probably in more detail in another video. But I'm going to go a little bit brief here what it does. Let's go check my website for what it does. And so this is what I meant by add the protein DNA complex to another particle set. So as you see in this image, we have the DNA molecule masked as a whole. That's in our default particle set. That's what we do particle analysis for, right? To identify the DNA molecule, the protein DNA bond molecule. And in the script that I'm describing, right, so you can use that script to crop the protein DNA complex into its localized neighbors, right? So you have this protein with a part of DNA arms on two sides. So we're going to use that and add these individual complexes to another particle set. And with that, we can do some very cool stuff like particle classification. So in this case, I cropped all these protein DNA molecules. I can put into a particle classifier, right? And then I can use the automatic classification algorithm, right? So I can analyze, right, and classify them into different classes, right, groups here. So I have this 0 band state, like 30-degree band. So classify them by their band angles. So the program automatically does that for you. So that's the purpose for this script. So all right, so script I'm describing is this. So, and when you right click this table, there's a casting operation. Right here we have this mask protein DNA from XY. And remember the XY information we recorded earlier here in these two columns XY. They are important, right? This is used to mark the protein location on the DNA, in this image. So we use that information to mark, to mask only the protein DNA complex, right, without masking the whole thing. So what I'm going to do, I'm going to click this. So now it brings up a separate window, and you can add particle. It's called add particle to particle set, right? So we have our default set and also create a new set. So the default set stores our the DNA information, right? DNA analysis, which is like here. So we go back to image processor. We have the default set here. That's where we did our particle analysis that masks the whole protein DNA complex, right? The whole thing. So we can create another set. We can create either here, create a new set that only that only has the localized protein DNA complex in this new set, right? So let's go back to here. So okay, so right now I have 4 particles, which basically 4 of the protein DNA complex, and I already specified a parameter as such that it's going to take a little bit of DNA. It's basically like quadruple the area of the protein complex. So like by that, it can basically enlarges the mass of the protein so that it can encompass a bit of DNA arms. So like it is defined as a circular mass with quadruple the area of the original mass, which is the protein complex. That's why you see a little bit of DNA arms also cropped. That's exactly what it wants, right? We needed this DNA arms in order to classify its bending, right? DNA bending classification, as you saw earlier. So right now I have 4 particles, and apparently 2 of them, they belong to the same one. So because they're too close to each other, so their mask overlap. So essentially they merge into a singular one, right? So in this case, it's useful to analyze them in combination, right? So like they're not necessarily separate from each other. I mean, you can also separate them by yourself later on, but right now we can just do them as one. And that's useful for coordination events. Essentially, if the protein can signal to nearby proteins, right? This is useful for to classify those situations. So we have like 3 particles, and the 3 and the 4 one are essentially the same. So I'm going to just click add, and before that, let's create a new. You cannot add them to the default, like the current particle set you are in. So we should add them to a different set. Let's call it PD complex. Okay, that's what we want. Now the default set is really just the DNA analysis that we just saw, right? And the new set, right, that only contains the protein DNA complex, the localized one, right? Not the whole DNA. So let's click OK and click Add. Now you still see there's a table on the right side, which is essentially the same information as you see here. So this is the particle 1, which is essentially, the row 1. Okay, 137 degree in the angle, right? So height is 1.96 nanometer. That's corresponds to row 1 here. If you go to particle 2, that corresponds to row 2, 139 degree. So you get the idea. So I'm going to click Add. Now it's going to complain about the number 3 and number 4 because they're the same particle, right? So they say this particle mass is already occupied by an existing particle because 3 and 4, they're the same. So we can simply skip that one because I only need one of them. So now it's added to a new set. Though you can see the result in the image processor. Just we know that it works, right? So here we have default set. I just create a new set. It's called PD complex here, CC. I also create it here. So let's go to the PD complex and see if that works. And it should only see the protein DNA complex of this molecule. So see how so 1, 2, 3. Now 3 is the 3 and the 4, right? They merge into 1. So we have 3 particles. This is like a manually created particles, right? So previously in this default set, we do this in Bark, right? In this traditional particle analysis sense, right? Now these 3 particles we just manually created from the region inspector. So let's go back to the default set. And with these 3 particles, right, so the manually created one, then we can input them to the particle classifier. So that's the ultimate purpose, to classify their conformation of these protein DNA complexes. Okay, let's go back to default set, and then we can go back to the region inspector. So now we have analyzed the first DNA molecule in this particle, particle 1. But we have another particle, another DNA molecule in this particle 1, right? So this is particle 1 here. So as you see here, right, we have another DNA molecule, so we're not done yet. So let's click the secondary DNA molecule. And yeah, we have to redo the mask for now. And if you see, why I cannot click this one, it's because right now the mask is only localized to these 3 particles. That's what we did with our script, right? It tried to crop these masks, that mask, and I mean, into the 3 individual components, right? So now we have to redo the mask. Let's just click auto mask. So go back to yeah. So let's click this molecule and just do the same thing. Move this into the bottom edges, and then yeah, let's click and record a new blank measurement. If you don't do that, right, the measurement will add on top of the original one. We don't want that, right? This table right now is for our record 1. We need to create a new record, right? So let's do a new record. So let's start a new blank measurement. So let's do the same thing, repeat that, and the find peaks and spans, click that. So then what we do is, let's zoom in this a little bit. Let's draw a region of interest. Now let's measure the volume of the protein complex here. Record all volume. Record all parameters. Okay. So now as you see, the automatic calculation for PD type, right, the protein DNA type, it says one of them is a specific complex. The first one, this one is a specific complex. And that's because if you look at the short arm fraction, it's 35%. So it's within our error range, right? From 35 to 39%, right? That's our the DNA slip out, where the specific site is, right? It's plus minus 5%. That's how I set my parameters in this script. So that's classified as a specific complex here. So let's go on to measure the band angle. So here we only need to measure the first one because the second one is an AND particle, and then we can simply type the conformation as AND here. And let's do the same thing. Mask the protein DNA from XY and add them to a different set, right? So you see, this is the whole thing, right? The protein with its DNA arms. We're going to do a particle classifier with this after we add them to a new set, right? So let's click add. So now it just record current measurements. So that's something you should remember to do. Now, if you don't do that, the program will remind you to do that. For example, if you X close this program or move to the second particle, the program will remind you to do that. So for our record, let's just record current measurement to make sure that the label is nearby the DNA molecule. Yeah, here it is. So yeah, we have done that. And remember, we already checked autosave. So when we move to the second particle 2, right now we are at particle 1. Okay, there's 2 in this particle 1, right? This whole masked thing, right? There are 2 DNA molecules, right? So remember, we are doing single molecule analysis, so we have to move from 1 to 1, right? And so what we're doing is like essentially semi-automated analysis, right? Assisted analysis. So it's not completely automatic, but with the current algorithms, right, scripts, it really helps us move very fast in in this kind of analysis. So let's just move to the particle 2 here. Just you can either click the list or you can also click the left, the arrow keys. And since we already checked the autosave options, the program will remind you to save that. If this is the first time you analyze the molecule, this is the first molecule, right? Then it will ask you to save to a file, right? So at that, you only need to do this once, because after that, it's going to save all the additional analysis into the same file. So we only need to do this once. So let's just go somewhere and make a new folder, and let's call them. I think it's A6B. Let's call that. Okay, and we have the name here. Let's name it analysis. Okay, click save. We're going to see what the file, what the content of the file is later on. So right now it's saving the table into that Excel file. It's also saving the snapshots, and it's also going to save the crops, which is a rectangular box that specifies the region of interest, which is this area, right, in the main image, and you can see them later. Now to check out whether our files are saved properly, you can go to a File Explorer and check that. A6B. Now we have the Excel file here, and yeah, we'll check them right now. And I also have the snapshot that we did. Let's check that as well. Now let's see the snapshot. This is essentially the analysis that we just did, right? The original image, also the measurements that we took, and we have the trace, okay, and the length of DNA and the table of that. That's the snapshot. So you can use that as a reference in the future, right? You can look at a table, your data, and see, okay, how did I do my measurement? So this gives you an idea, right? So it saves that as a snapshot. And then let's look at a table. So remember we have two records, right? So let's first locate the record column. So here we have one record, two record, right? So in the first record, right, remember we have four proteins in the first DNA molecules. That's why we have four entries or four rows. So the row or the entry number is recorded in the entry column, which is here, like 1, 2, 3, 4. That represents the four proteins, right? And we have the second DNA, which is like there are two proteins on the second DNA, and then we also have one end binding for each particle. So that's how the table is arranged in this Excel file. So right now we have our essentially it's particle one, right? So this is our particle one, which has two records. We go to the particle column, which is, let me see. Yeah, it's in the end. So we have the image column, right? The image name, the particle column, that's particle one. We also have crop column, which is the crop one. And it's also named here, like particle one, crop one. The crop one specify the DNA regions. So if I simply zoom out, let's see. So you see here, is crop one, which this is the green box that specifies, right, crop one that I just mentioned. That's our crop one. That's what it means, right? That's our molecule. It basically draws a region of interest, rectangular box around our particle one. That basically means I have already analyzed this particle, right? I finished that, and the program gives you a label, right? Labels with this crop. So in the future, you know, okay, we have already gone through this particle, and when right, we're done with this particle, right? Basically, then we can move on to the next particle. And you get the idea. So if you have analyzed another particle, let's say the 14, now we're going to make a crop on that one as well, right? So as long as you have checked these an autosave option, I just checked these crops, it will save that crops in your main image, right? So now we are at particle 2. Yeah, so this one, let's see. So I'm going to cover a little bit more additional topics on this one. So remember, originally we have the DNA masked pretty well, so it's well connected. And what if the mask is not so good? It happens if you have a noisy image. If your auto mask algorithm is not doing so great, or maybe the image is so noisy you can't really connect the DNA well, right? Because the DNA is very low signal to noise ratio, and that can happen, right? So your DNA is basically disconnected in terms of its mask. So let's say that. Let's artificially do that by increase the mask threshold. Now you see it's already disconnected because you can tell by that color, right? If the masks are disconnected, you see them in two different colors, right? So further do that. Okay, now I have three, maybe four components here, right? So okay, so let's say this is the case. So imagine we have a very noisy image, right? We'll do the auto mask, it still does not connect the DNA well, right? Still, it's truncated into like several pieces. Now we have a new tool. I mean, we have a tool to connect these masks, and it's called the link DNA. So if you click link DNA, this is essentially you can find the mask under morphology. Let's go that. So you can either do that from here. Let's click morphology, and then click profile. There's link DNA, right? So So right now, let's click link DNA. Yes, and you see that it's connected, right? So that's a very cool trick. So now the other way you can do that, let's go back to our mask again. Let's go to auto mask, down a few things. Oh, that's too much. Okay, let's give them some example here. The other thing you can do that is to manually link the masks. All right, this is like an automated feature. Like just click link DNA, it will connect the DNA for you, right? So the other way to do that is to manually draw a mask. Now to do that, you can use the mask eraser tool. So under mask menu, there's a toggle eraser mode. You can just click that. Then you can also map that to a keyboard shortcut, which I already did. So here I map that into a Control E. Now you can do that as well. You can simply go to the miscellaneous tab. You can click manage and click keyboard shortcuts. Then you can search for the tool, which is called toggle eraser mask, and then map your keyboard shortcuts there. So right now I'm just going to press my keyboard key, Control E. So you see the mouse turns into a circle. There's a circle in the image, right? That's our eraser. That you know it's in the eraser mode. So in this eraser mode, okay, there's a few things you can do. So if you simply drag your mouse, press and drag your mouse, it's basically making new masks. For example, like I say that, drag these. So it makes a new mask, it connects the DNA, right? And the other thing you can do is you can, if you press Shift and then press and drag the mouse, right? It's in the eraser mode, right? It erases the mask, right? Now you can also undo and redo here. Use this button here. I already mapped them as well. Undo is Control Z, redo is Control Shift Z. You have to manually map them into the keyboard shortcuts. Right now I'm just showing you, I say undo, and then it restores the mask, the last step of your masking operation. And then you can also do that, make the eraser big or small. So you simply hold Control key and scroll your mouse wheel up, which increases the mask eraser size. If you scroll down, it decreases the eraser size, right? That's how we have to do that. All right, so that's that. So we already connected our DNA molecule using this eraser tool. So you press Control E again, it toggles that mask mode, eraser mode off, right? Now you can simply click the DNA molecule. Let's turn on transparency. So that's how we do for disconnected DNA. So right now, let's repeat the same process. Since this is a two pieces of thing, and so there's one thing for this specific molecule that I did not pay attention. Let's repeat the same process. Yeah. So you see that there's the DNA actually is not traced exactly like this, right? So there's a bit of DNA here. So the DNA basically goes inside, maybe it goes out again. So maybe this is not the end, but this is the end. But if you actually do that, the trace right now is not passing through the second molecule. As you can see, there's only one peak instead of two. Now you have to force your way inside that protein complex, right? To do that, you can simply, there's two ways to do that. The program has two modes of tracing. In terms of automatic tracing, right, there's two modes. So one is you simply click this molecule, so it determines the, so I call it like, I'm not sure what mode I should call it. But basically, when you click that, it determines the the starting point and the end points, right? So this anchor point is always the start, right? This anchor point is always the end. So what you do is you move the end point into the real end, right, which is here. Then you can add middle points between these two. So I want to add a middle point here, right? So I just simply double click like somewhere here. So as a middle point, so now that your end point, right, originally is the second point, right? Now it moves further down to the third point, and that becomes the end point, right? So that's how it does. So move from point 1 to point 2 to point 3. Now we have two peaks along my trace. Now that's the first way to trace this DNA molecule, right? Now the second way to do that is to manually trace these, like from point to point, like one by one. So to do that, you first, without selecting the molecule, you first just double click the first anchor point. So for example, here, let me just first double click that. And that's my first point. Now you see there's only one point here. So I'm going to add my points one by one along the trace. For example, I want to move here, and I double click that, and I move here, double click that, and finally move to my ends, double click that. So that's how I do it the second way, which is like the sequential mode. I call it sequential mode. Yeah. So from the first point to the last point, and the first mode is the middle point. Middle point mode. You can call it that, right? So the program determines the first and the last point, which you can manipulate, and then you can add the middle points in between them, right? The midway mode, I guess. So yeah, right now I can move these a little bit just to make sure it reaches the edges of the protein molecule. Yeah, I prefer that because it gives me more information. For one, because I don't necessarily know where the peak of the protein is. And if I move to the edges, and I can identify exactly where the peak is. Now, if you want to do further measurement, like maybe the DNA does not start at the edge, but start at the peak point, right? You can just subtract this whole length of the trace, right? You can subtract the these initial parts, right, from the zero to the peak, and subtract that from the whole DNA length that you measured here. So right now we have these traced. Now I can simply repeat the same process, like find peak and the span. All right. So let's say, okay, it finds the exit and entry and exit points for particle one, protein one. That's good. And for protein two, let's see how well it does. So right now, let's see. Okay, so 1 to 2 to 3. So this point should be the entry point should be 4, right? So it'd be like this. Start from here, and then it goes to 5, which is the peak point, and 6 is the exit point. So 4 and the 6 essentially they overlap. Okay, so that's that. That's really good. So that's exactly what we want. Okay, now we have these. We have two protein complex, so we have two rows in the table. The program does that for you. And then I'm going to do the same thing, draw a region of interest. So we want to get the volume and the height information from this complex. Okay. Draw a region of interest. Now remember that the color of these marks that corresponds to a sequence in the table, right? So this would be the first protein, and this would be the second protein. Now, since I have done that, let's go and measure the angle. And for this one, it's really difficult, and I don't really know how it goes inside of this protein complex. So I know this part, the exit, should be this way, and the entry point is probably the same. Let's just say it's the same, right? It's probably the same. I don't really care. In this case, it's really hard because it clearly should. It's definitely not going that way, right? Because that way it doesn't go through the protein at all. Because we have limited information in this image to determine its exit, direction and entry direction. This is just our best guess scenario. And so we want to separate them out, right? So this is not exactly great quality angle measurement. So instead I was saying like I add to my angle one, which I would prefer to be my highest quality angle measurement. We can simply add a different column of angles. Let's say we can add two columns of angle. Like for this column, this is angle one, right? That's our best quality angle measurement. That way I can add another angle measurement. Let's say, let's click that, right click that, because we just added two columns. I will say add to angle 2. Now I have to select the second row because that's the second molecule. Now we have like a different angle. Yeah, it's here. It's angle 2. So, all right. So that's that. And in this case, this first one is the end molecule, and you can, yeah, I will continue to do that. Let's just add them into my um, let's add them to my protein DNA complex particle set. All right, so let's do this. Mask on XY. And I should be good. Let's just click add. All right, then I can move to the third particle. Um, yeah, since I forgot to record the particle, the program will remind me, say, the current record saver is not empty. Do you want to save the records, right? Click yes. It will place a record label on this DNA molecule. Yeah, now it's giving me an error that says it cannot write the table. And the reason for that is because I have opened my Excel sheet, right? And you cannot have it open and write the table write to the same file at the same time. So I have to close this file first, and I will have to repeat the same process again. So let's go ahead and click this again. Just repeat the same process. So now we are at particle 3. Okay. So let's go back to see if the error that just the program gave me gives me real trouble or not. Let's go back to our image processor. So we are at particle 3, okay? Let's see how many crops we made. We should have made only 2 crops. Yes, we have 2 crops here. Right. And let's go back to our image. Yeah, because I think they just throws me an error. So the crop 2 and the crop 3, they are in the same place. So what do you call crop 2? Right now it's crop 3, so they overlap one another. And that's fine, it doesn't really cause any trouble. And then the image snapshot that we have is already named crop 3. That's fine. Um, yeah, just remember if you open this Excel file and edit at the same time, the program will not save. It will prompt an error, so you have to close that file before it can be saved. So I think this it does. Let's you can double click that and check the results, right? So that looks good. And then we can go back to our Excel file again and see the result. You don't have to do this every time. I mean, I just only do this. I mean, after I finish all my analysis, basically. I don't know, maybe I'll check it once for a while, but just remember to close that file. So right now I see if my measurements are recorded into this file or not. And let's go to the particle 1, particle column. Now we have particle 1, particle 2. So that's good. In particle 2, right, we have 2 entries, 2 proteins essentially. So we have entry, which is 1, 2. And the crop, as you see here, is like it should be crop 2, but because it shows me an error in the middle, right? It already made a crop 2, right? So, but it fails to save crop 2, right? So now when we save it again, it tries to make a new crop. So that's why it ends up in crop 3, and it's not a big deal. And the basic idea is once you have this table, right, you can, okay, you have this information, you want to say, okay, what is the exact condition that I made my measurements. I want to trace back to my regional measurement, right? So this gives you the information for us to trace back, right? It tells us, okay, this is in crop 3, right? And this is in particle 2. So we can basically use this information and navigate to our snapshots, right? So this is particle 2 and the crop 3. So essentially that's the measurement that we made back then. So you just open up the snapshot and you can see how we did the measurements, right? No. So from, yeah, that's how we do that. So yeah, let's go back to the region inspector. Now we are at particle 3. Now you just basically repeat the same process for all 120 particles. And after done that, then we move to the next image, right? So, and then repeat for all the images. Now you may ask, what should I do if I want to take a break? For example, if I want to shut down my computer, go to sleep, and so can I come back to the current state and continue my analysis? Well, the answer is yes. So to do that, you go back to the image processor, and this should be something you should do like immediately right after you finish the image processing. So after you've done the automated image processing, right, analyzed all the particles, right, the DNAs, and what you should do is you should click these save button, and it will ask you whether you want to save the snapshot with region of interest labeled as well. And I usually would say yes. So we take a snapshot of your main image essentially with the crops as well. So I'm going to save this to the same folder. Now they ask me to save the workspace file, and this is a file with an extension called IM. Let's save that. Now, as you can see, it's saved into the workspace file, and also this file is our the snapshot of the whole image with the crops. So you can see that the crops are here, the green boxes. All right, so let me just demonstrate quickly, and so what happens when we load our images back? Okay, so let me go ahead to close all these windows. Just say, okay, we started fresh, right? Can we load them back? Let's just do that. We already saved that. All right, so to do that, let's just boot back into image processor. So now we just double click this file, IM file. That's our workspace file. Now it's loading that into the workspace. Okay, so I think we start at 5. There we go. You can see that we have our crops 1, crops 2, and 3 here. So exactly where we left at last time. And then we can go back to perform the region analysis. And you can also see that we have our particle set here as well, the PD complex and default set. And yeah, before you close, every program, just to remind you, right, it's best to, just save that again, right, because it won't autosave for you. just before you close everything, just remember to save your workspace again. Now, if you really forget about that, right, the program has auto recovery features, so you can basically load your last analysis back into the workspace as well. So you can basically do that from the results table and say load results. And you can find the auto recovery files under your documents. And I would cover that in another video. So basically, there's the safety measures, right? In case you really forget to save everything, right? So that's the safety measure is built into this program as well. So now let's go back to Region Inspector. Now remember last time we are left at particle 3. Now you can also navigate the regions, right? We're left at region 3 essentially. And region number 2 and 3, the crop is basically crop 2 and crop 3, they're the same. Just remember last time we have we just couldn't save into crop 2, right? So they're essentially the same. Yeah, this is essentially particle 2 here. Just for your information, you can see that. You can navigate your saved crops if you check this box. All right, these are the particles, the regions, right? You are analyzed. Now that's an easy way to go back to your particles, right? That you have already analyzed. Now we are at particle 3, right? So the particle 2 should be the region 2 and 3 here. That's the same, right? So we are at particle 3. Yeah, that's where we are at. So now we can continue our analysis starting from here. Now the only thing different is after you finish analyzing these, right? It's going to ask you to save to the file again. Now in this case, you just basically pick the same file, right? Well, you're not going to overwrite that file. Essentially, it's only going to add new information to the bottom of that file. That Excel file. Just I'm just going to do this very quickly. I'm not going to do a real analysis. Just do a fake analysis. Let's say I have these molecules, right? I just want to record all the properties of the DNA as a whole into this one row table here, right? And then move to the fourth particle. Let's assume that I already finished analysis of this particle, which I didn't, but just for a demonstration how the save works, right? So this is we are at a new session, right? So the program won't know what file you're saving to, so it will ask you again, right? So for right now, I'm going to navigate to the next particle, right? It asks you to save that because I didn't record my particle, right? So I'm going to say yes. I'm going to save this record, and now it's going to and ask me to save as a file, right? This is the file name that we last saved to. And you just click the same file and click save. It says it will replace that, right? Well, in essence, in reality, it won't, right? It simply adds new information to the bottom of this Excel file, right? So let's say click yes. Now it's doing the same error again because our Excel file is open. So I have to remember to close that one. Yeah, we can basically make the same mistake. Let's repeat that process. Yeah, just remember to close the Excel file. If the file is open, you cannot write to the file for some reason, but that's that's the reality. So yeah, now we have saved this to the file. We also have saved another snapshot, which is called particle 3 crop 5. Now it skipped crop 4 because now right there we have a count. We couldn't save the crop 4 because the Excel file is being opened by Excel, right? So we can't save the Excel file. So it moves to the crop file, which is fine. So we have particle 3 analyzed, okay? And let's see if it adds to the bottom of the Excel file. Now we see that this should be our crop file. You see that? This is the particle we just analyzed. Particle 3 crop file. That's exactly that. It's just one row. This is the one row new information that we added to our Excel file that we saved last time. Now it's adding new information to the same Excel file, snapshots of that as well, right? So yeah, after finish a new round of analysis, maybe another 20 particles. Now you feel like you're done for today, right? Then you can just go back to image process and click save again. Just save the workspace. And that's all you need to remember to do. Now, if MATLAB crashes, right, you can forget to save that. Like I said, you can easily recover your last analysis by loading back the results, right, from your recovery files. So, all right, I think that's pretty much it for this video on how I use image metrics to analyze protein DNA complexes. Thanks for watching.